Well, hello and welcome everyone to the Andlinger Center's Highlight series. I'm happy to welcome you to today's Environmental Highlight seminar by Professor George Tynan on how might controllable fusion fit into the emerging low-carbon electricity markets of the future. I'm Jesse Jenkins, an assistant professor here at the Andlinger Center in the Department of Mechanical and Aerospace Engineering, and it's my pleasure to MC and host Professor Tynan today. I wanted to note in that role, I will be moderating questions both from our live audience at Mader Hall in the Andlinger Center and via the Q&A window of our webinar for our webinar participants here on Zoom. And George will be able to answer those questions after the conclusion of his presentation. So I'm excited now to welcome George Tynan with us. George holds the Kazuo Iwama Endowed Chair and is a distinguished professor of engineering physics in the Mechanical and Aerospace Engineering Department at UC San Diego's Jacobs School of Engineering, where he also currently serves as the department chair. He received his PhD in 1991 from the Department of Mechanical, Aerospace, and Nuclear Engineering at the University of California, Los Angeles. He then spent several years studying the effects of sheared flows on plasma turbulence and experiments in the Federal Republic of Germany and here at Princeton's Plasma Physics Laboratory. He then worked in industry developing advanced plasma sources for use in semiconductor manufacturing and joined the UCSD faculty in 1999. His primary research focus is on the physics and technology issues that must be resolved to enable energy generation from controlled nuclear fusion. He studies both the fundamental physics of turbulent transport and hot confined plasmas using both small-scale laboratory plasma devices and large-scale fusion experiments located around the world. In addition, he's investigating how solid material surfaces interact with the boundary region of fusion plasmas and how the materials are modified by that interaction, important aspects of developing a practical fusion power plant. He's also interested in the larger issues of transitioning to a sustainable energy economy based upon a mixture of efficient end-use technologies, large-scale deployment of renewable energy sources, and the incorporation of a new generation of nuclear technologies such as advanced fission and/or fusion reactor systems. He also co-directs the UC San Diego Deep Decarbonization Initiative. I'm excited today because Professor Tynan's remarks are remarkably timely. The field of fusion is growing like we've never seen before as it transitions from a long period of critical fundamental science research to a focus on practical commercial applications in the energy sector. Beyond the large-scale ITER project in France, the US Department of Energy and European agencies are both focused now on more rapid deployment of a pilot-scale fusion power plant, with PPPL here at Princeton taking on an active role in these developments. At the same time, we've seen multiple private sector companies which have collectively raised billions of dollars from investors to develop fusion power plant technologies. In fact, just last week, Commonwealth Fusion, based in Cambridge, Massachusetts, raised $1.8 billion to develop their advanced tokamak reactor, which is intended to be enabled by a new electromagnetic technology with unprecedentedly high field strengths. All of these efforts are looking at deploying a practical fusion power plant within a much more accelerated timescale of a decade or two, rather than the mid-century timeframe consistent with the current plans to progress from ITER to a demo plant and on to commercial reactors. So with all of this, it's critical that we take a broad look at how fusion can fit into a rapidly decarbonizing electricity sector. Fusion's not the only option we have to fill the critical role of clean, firm power generation. So the energy systems and fusion research communities need to collaborate to identify the cost and performance characteristics for commercial fusion that will enable it to play an impactful role in our energy future. That's exactly what we're doing here at the Andlinger Center and PPPL in a project led by Egeman Coleman and myself, and what Professor Tynan and his colleagues have been thinking deeply about in his roles at the UCSD's Center for Energy Research and the Deep Decarbonization Initiative. So without further preamble, I'm delighted to welcome George Tynan to the Highlights seminar and excited to hear what you have to say. Thanks for joining us.
Thank you very much, Jesse. Just want to confirm before I get going, are you seeing my slides without any difficulty?
We are here on Zoom, yep.
Okay, great. So it's my pleasure to be here, and I want to thank Jesse and the whole center for the invitation. I also want to acknowledge some very useful interactions I've had with colleague Ahmed Abdallah, who's at Carleton University in Canada, and David Victor here at UC San Diego. So let me give just a few background comments about fusion, just to make sure that everyone in the audience is on the same page about what we're talking about when I say fusion energy. Fusion involves combining two light nuclei, usually deuterium and tritium, which are isotopes of hydrogen, into helium. That nuclear reaction releases a very significant amount of energy. However, to overcome the Coulomb repulsion of the two nuclei, it requires very high kinetic energy for the ions. And that translates to a condition that the fusion fuel is at high temperature, about 100 million degrees Kelvin, or roughly around 10 kilo electron volts. Electron volts are usually the temperature units that we in fusion typically use. That means that the fuel will be in the plasma state. You all are familiar with the solid, liquid, and gaseous forms of matter. And the plasma state is what happens when the mass gets so hot that the electrons and ions in a molecule or atom are ripped apart and the system becomes ionized. So we have to talk about handling matter in this new state called plasma. In order for any fusion system to produce net energy, that is more energy out than it took to heat in the first place, we in fusion have this ratio we call the machine energy gain, capital Q, is the ratio of the fusion power divided by the input power. Obviously, that quantity needs to be bigger than 1 to have energy break even. And when you work out the physics of a power balance in a fusion system, what it means is that the product of the density of the fuel, which we use the symbol N, the temperature, capital T, and the energy confinement time, tau E, the so-called triple product, has to exceed a critical value, which for the easiest fusion reaction, deuterium-tritium fusion, is a few times 10 to the 21 keV seconds per cubic meter. So you can think of this essentially as the pressure of the fuel times the energy confinement time. And the energy confinement time is simply a measure of, if I turned off all heating systems, what is the time scale it would take for the fuel to cool off? And so in practical terms, this requires a plasma pressure, NT, of a few atmospheres of plasma pressure and an energy confinement time of order 1 second. And I would also point out, if you actually want to make useful electricity, this ratio must be much larger than 1, probably 10 to 20 at a minimum for a practical fusion power system. All right, so that means that there's a quantifiable criteria we can use to see how close we are to fusion conditions. As an aside, I will say there are 2 main approaches for fusion. One uses very high power pulsed lasers or other pulse power systems to compress a small sphere of fuel to very high density, and at which point you ignite a fusion reaction. This approach has been recently shown has really recently approached ignition conditions in experiments at the National Ignition Facility at Livermore. Time constraints don't really allow me to go much into ICF today, but my comments, I think, are germane to this approach as well. The other approach for fusion is to essentially create an endless magnetic field, which really means a toroidal or donut-shaped magnetic field to trap the hot fuel, the plasma. And so I'm showing a very schematic view of one such approach called the tokamak. Here, the purplish pink represents the plasma state. The green and blue, the blue coils are toroidal magnetic field coils. There's a current that flows in the plasma, shown by this arrow, which then makes a secondary magnetic field. And the combination of these different field components makes a stable closed magnetic field geometry, which can trap the fusion fuel. The first hot confined fusion plasmas were achieved way back in the 1960s. This is a photograph of the T3 tokamak device in the USSR. You can see the device over here on the right. You can see some technicians here for scale. And that device achieved plasma temperatures of around 1 kilo electron volt and caused a reorientation of most of the world's fusion program to look at the tokamak approach. The energy payback on this, however, was much less than 1. It was about 1 in 10 million. So for every 10 millionths of units of energy in, it produced 1 unit of heat back out from fusion. So clearly, there's a long way to go from this experiment to fusion conditions. If you look at the history or the family tree of tokamak devices as a function of time, that initial device is down here in the lower left in the early 60s. And you see this plethora of machines that have been built over the ensuing decades. And a couple trends you notice that as time goes on, the devices tend to get bigger because these are all roughly to scale, and some funny shapes of the cross sections emerge. The shapes are emerging because of a desire to maximize the pressure in the plasma. And the larger device is emerging really because that is how we found the physics necessary to get to the required energy confinement times in this particular approach to fusion. And so this shows the interior view of a currently operating experiment, the JET tokamak in the UK. On the left is what the device looks like when human beings are inside doing maintenance. So you can see this person inside for scale. And on the right-hand side, you can see what it looks like in operation. So clearly this is a much larger device than that old Soviet machine I showed you earlier. And the trick now in the key physics thing that we're going after in the fusion research community is to reach what's called the burning plasma state, which is illustrated by this rather complicated cartoon. I'll just suffice it to say that the burning plasma state is the condition when the plasma heating is dominated by fusion product heating and not by external power input. And so the frontier of fusion research is getting into this burning plasma regime and then studying and understanding how the fuel behaves when it is burning. We have demonstrated significant fusion power production in the research community. That first happened right here at where you all are at Princeton back in the 90s on the TFDR device. For a brief, about half-second period of time, they produced a bit more than 10 megawatts of fusion power. And then in subsequent experiments in the late 90s on JET, they produced fusion power for several seconds at about 5 megawatts, and then a brief burst of fusion power at about 16 or 17 megawatts of heat release for about 1 second or so. I'll just add parenthetically that JET has now started a second DT or deuterium-tritium fusion campaign this year. And we're waiting for results from those experiments in the next few months. On the right is an image showing data of measurements of the hot fusion products. These are called hot alpha particles. Really all they are is very energetic helium atoms or ions that are flying around in the plasma. And they tend to be trapped in these orbits that look sort of like a banana. Hence, we call those trapped particles that are moving on so-called banana orbits. But the bottom line is we are beginning to explore the fusion self-heating regime. These experiments, however, have not quite reached the conditions for energy break-even. So if I step back and I look at where the fusion research community has gone in getting to fusion conditions, on the vertical axis, we show this so-called fusion triple product that I introduced earlier. And the horizontal axis is the ion temperature. All those old experiments are all these various data points here. These curves of sort of salmon or mauve colored contours are showing you the energy breaking even curve, that is capital Q is equal to 1. And the second curve is where the so-called ignition condition, where the plasma can produce enough heat to sustain the fusion reactions by themselves with no external power input. The community is now designing a device called the ITER, actually building a device called the ITER device, which is expected to sit here at around Q of 10 and begin operation in the next few years. So just to put it in scale, that old tokamak device, here's a picture again. And if I shrink that to roughly the same scale as the ITER device, then this little postage stamp here in the lower left is that first generation tokamak experiment. This is a computer rendering of a cutaway drawing of ITER. Here's a little human being here in the lower left of that drawing for a sense of scale. And ITER is not just a computer rendering anymore. This is a photograph taken from the ITER website from a few weeks ago, showing the several sections of the vacuum chamber that are being assembled into the toroidal device. And again, you can see a human being here for a sense of scale. So conventional superconducting magnet tokamaks are these, I was called the standard approach to building a burning plasma device. This technology results in a very large scale system that has to be assembled from many, many large components that are manufactured elsewhere. If you step back, pardon me, if you look at the fusion community has done many reactor design studies over the years. If you look at one of the more recent such studies published about 14 years ago by colleagues actually out of UC San Diego, you get you can see the cross section of the device, and again you can see a human being here in the lower left. So we're talking about very large scale systems with a diameter of something like 30 or 40 meters and a height of something comparable, assembled from components that are built elsewhere, shipped to the site and assembled into a large system. So that's my overview of fusion systems and what we think a fusion reactor based on technology as of the early 2000s, what it would look like. The main point in this talk that I hope to convince you all of, or the main thesis, if you will, is that changes in the electricity market and large-scale cost reductions in renewable technologies are going to require radically different fusion energy systems from what we have imagined in the past. That is, if those systems are to be economic and to find a place in this market. So let me walk you through my reasoning behind this conclusion. So the talk is really organized into 5 main points. Talk briefly about restructured electricity markets, review the cost reductions in renewables. I'm not going to talk too much about energy storage systems, but suffice to say, significant cost reductions are also occurring there. There are important effects that occur when you integrate large amounts of renewables into these new markets. So I want to talk about those integration effects. This is not the engineering and power system stability. These are economic effects. Review the need for firm zero carbon generation. And that point is borrowing very heavily from Jesse Jenkins's work. And then finally close with some discussions about what a competitive fusion system might look like. So let's talk briefly about the restructured markets. The old way of thinking about electricity markets was a very large utility that owned the generation, transmission, and distribution system. So they basically is a vertically integrated utility system. In many parts of the world, this structure is still used. In Europe and in many parts of the US, we've moved away from this organization. And then a regulator, some sort of utilities commission, sets the tariffs that allow the utility to make a reasonable profit at a price that customers are willing to pay. And so the traditional fusion reactor concepts have aimed to substitute largely for these conventional large-scale centralized generation systems. And so if you look at, for example, the tokamak design study that I referred to earlier, this is a device with a of 25 or so meters, a power rating of something like 1 gigawatt of electricity that would be produced 24/7, operating more or less as a baseline power generation. This is in the magnetic fusion approach. And if you look at the reactor studies, I would say are not as mature in the laser fusion approach. But if you go back into the older literature, you'll find descriptions of inertial confinement fusion systems. This is frankly the best drawing I could find from one such reactor design study. But here is the core of the fusion core of that system. And then the whole thing is, a couple hundred meters, 100 meters or so in scale. So very large system producing of order a gigawatt of electricity, about 3 megawatts of heat power, using a Rankine steam cycle for power conversion. So both of those approaches traditionally have aimed to simply replace the large-scale centralized generation in the utility model with a fusion system. However, in many places around the world, the markets have been radically changed. And instead of one entity owning the entire system, the generation is owned by one set of entities. The markets are operated by a second entity, usually some sort of public entity. And then the transmission network and distribution is owned by yet another entity. And the system, and then a retailer basically bundles the services of the distribution system, the system operator, spot market operator, and the generator system to actually deliver power to a commercial or a residential site. And so the key thing to note is that these various elements of the energy system are owned by different entities who have different economic motivations. And so the generation is no longer going to be owned by the transmission system, the entity that owns the transmission system, nor the distribution system. And this leads to a radically different behavior of the market. These deregulated markets have been adopted quite abundantly across North America and the US, and they seem to be growing over time. And so they're an important consideration when you're thinking about how will a new energy technology move into an economic market at some point in the future. These are the markets in which fusion will have to be competing. The market fundamentals in these liberalized or restructured markets are the basis for all of the energy prices, both short-term and long-term. The costs are generally based on the marginal cost of production, not on the average cost. And that results in very large and natural spatial and temporal variations in pricing. This is sometimes referred to as locational marginal price of electricity, which can vary by almost an order of magnitude or more, depending upon time of day, time of year, and location. And the primary goal of this liberalized market is to increase the efficiency and availability of generation and incentivize the movement to lower cost generation and transmission, and overall to have a system that's more flexible. So let's just look schematically. This is my physicist's understanding of the economics. So I'll sort of caveat emptor, I am not an economics expert by any means, but the price versus demand curve looks something like this. The red, this declining curve is sort of showing, pardon me, the satisfied demand is sort of in the red part of this curve. Unsatisfied demand is this black part of this curve. Generation technologies that are profitable at the equilibrium price at this particular point in the grid and this point in time, though that price is given by the intersection between the supply and demand curves. And so generators whose marginal cost of generation is below this equilibrium price will be priced into the market, and those who are generating at higher marginal costs are priced out of the market. And so at any given time, there'll be a sort of quasi-equilibrium established. And over time and at different points in space, this equilibrium price will move around. And so generation units will be turned on and off as the price moves up and down, as the supply and demand curves move up and down this curve. And so we should also note that there are multiple markets that one is interested in. There are month to years ahead markets. This is sort of capacity planning and transmission rights drives transmission and capacity planning rights. There are day ahead markets that are sold in typically a few minute, maybe 15-minute blocks of time. There are real-time markets that operate on a few minute time scale. And then there are ancillary markets that serve to maintain grid reliability and stability. This is for frequency and voltage regulation, maintaining sufficient operating reserves, capability for black start in the event of a blackout, and management of reactive power levels in an AC transmission grid. So that's just a very quick introduction to the restructured markets. Now let's turn and pivot to look at renewable generation, and then we'll look at how those two things play together. So you all know that the unit cost of electricity generation from photovoltaic modules and PV systems has dropped very significantly in the past few years. This is the so-called learning curve plot of the modular price dollars per, or in this case, euros per of power versus the cumulative installed production for solar. And so you can see this marked reduction in unit cost with a learning rate that is the slope of this line that's quite extraordinary, about more than 20% cost reduction for solar PV learning. And as a result, installed PV capacity has grown enormously. I should probably update this curve because this is now approaching more than 500,000 terawatts of installed PV capacity globally. Wind has been going through much the same phenomena, so I won't spend too much time here, but both wind and solar, particularly solar PV, have experienced very marked rates of learning, consequently rapid drops in unit costs, and very large growth rates of their installed capacity. The implication of this is, I just took this, this is from about a magazine in the power engineering community. This is about a year ago. The Los Angeles area DWP, Department of Water and Power, contracted with an independent provider to build a 400 megawatt PV station out in the Mojave Desert, about 200 miles from LA, and to have 3 hours of energy storage. So the 1200 megawatt hour energy storage system combined with the PV system at a contracted power purchase agreement price less than $20 per megawatt hour for a 25-year PPA. So if you think that renewables aren't a serious player, this fact of a recent result in that industry might cause you to look twice at what's happened in renewables plus storage. Very inexpensive power with reasonably high reliability for Los Angeles's power needs. So the mental model that has sort of emerged is that the levelized cost of energy from these renewables, say solar, over time has been going through this secular decrease in cost. Installed base of generation is going up, as shown by this dashed line, and the cost of conventional thermal generation from coal or gas have been relatively fixed if the fuel costs are fixed. And so consequently, solar has become sort of the cheapest energy generation technology in some regions of the system. And so the mental model is, okay, low cost variable renewable energy, VREs, are going to displace carbon-based electricity generation. In some sense, that is happening in some regions. This is a day in the life of the California system taken from CalISO, showing the 24-hour history of electricity supply and demand in California. Green is solar PV. The orangey curves are this light orange or rust-colored curve is the natural gas generation which you can see is traded off against solar. All these other curves down here are some base load. So this light gray is nuclear, black is coal that we import from our neighboring states, and so forth. And so you can see this 24-hour trade-off between generation capacity in the California system. And if you look at other systems where renewables have a significant market fraction, the week of generation in Germany, again, you see solar coming and going with the day. Germany has significant wind generation. And so you can see the wind is also varying, not so much on a diurnal or daily basis, but more on a sort of a weekly time scale. And then the other generation techniques, particularly the thermal systems, are being modulated so that the sum of all these generation techniques meets the time varying demand, again, in this case in Germany. So one might be naively tempted to say, well, let's just deploy solar and wind as much as we can, switch ground transportation to electric cars, and we've reduced about 2/3 of the emission problem, right? We're 2/3 of the way to a solution. As you probably guessed from the subject of my talk, the answer is not quite so simple. And that's because the introduction of large amounts of renewable energy also has a material effect on the price and on the market economics. If you want to think of this from a physics standpoint, there's essentially a feedback effect that when you introduce a whole bunch of cheap, time-varying electricity into the market, that actually affects the price of the electricity in the market. And that's what I'll talk about next. So just to remind you of the supply and demand curve that I discussed earlier, the demand curve intersects with the supply curve at any one point in time, and the intersection defines the equilibrium price and the amount of satisfied demand. And then as demand goes up and down, as this demand curve shifts to the right, that price will go up. What I want to now do is ask the question, what happens to the system if I introduce more power generation that has very low or even zero marginal generation cost? And so what that amounts to is this supply curve shifts to the right. And if demand is fixed, which is another assumption that I'm not going to dive into here, when you shift the supply curve to the right, by example, introducing a bunch of low marginal cost renewable energy, then the equilibrium price drops for a given amount of demand. And if you go look at the electricity markets around the world, pardon me, you will see this in action in those markets. For example, in California, if you look at the net load, that is the difference between solar and wind generation and demand in California, during the middle of the day, the net load is decreasing as the years go on because we've installed more renewables. And if you look at the price that energy has fetched on the market, you also see that it's dropped from about $26, $27 per megawatt hour. I should say that's the retail price. That's the wholesale price. I, as a customer, pay considerably more than that. But in more recent years, that price has dropped to about $15 per megawatt hour at the wholesale level. And so you might say, well, that's great. My energy is cheaper. Well, that's true if you're a customer. However, if you're in the generation business, you care very much about what price your energy fetches on the market. Similar effects have been observed in the German market. I'm not going to spend much time on this. Just suffice it to say that solar PV and solar wind have both had similar effects on electricity prices, the time of day pricing in the German markets as well. So the introduction of large amounts of low marginal cost variable renewable energy as a rule tends to suppress or push down the equilibrium price of the energy in the deregulated market, and makes life difficult for all the other generators who are essentially sitting higher up on this marginal cost curve. So if you're a natural gas vendor or a nuclear power plant and your marginal price is sort of in this range, you may be priced out of the market. And so the demand for your services is going to go down. And so that then now brings me to the fourth point in the talk, the need for firm zero carbon generation. And this really borrows, I have to tip a hat to Jesse and his work, which has influenced my thinking tremendously on this issue. Pardon me. Just to illustrate this, there's a very nice study that came out recently from Google. I've given you the reference if you're curious to go find this white paper out of Google. They have data centers all over the world. Google is very interested in at least looking green. And so they contract to buy large amounts of renewable energy so that they can brag that their company runs on clean energy technology. If you look at many of their sites, however, this curve is taken from a data site from Google, I believe, in South America. I think it's from Chile. You see these green spikes are this is a year's worth of energy demand at their data center. The grayish, charcoal gray, solid curve shows their steady state electricity demand. The green shows the carbon-free energy supply that's available. And so there are times when there's more than enough renewable energy, and there are other times when they have to go onto the on the market and buy carbon-based energy generation. That's, say, at these regions where the data center demand outstrips the renewable energy supply. This is another Google plot taken from a different data center, showing the effect of if they contract for carbon-free energy with the status quo at the site where this was located. I believe this is now in America. And so you see a year's worth of demand, and the gray regions are when they're buying quote unquote dirty power, and the green sections mean some fraction of their power is coming from quote unquote clean sources. In the status quo case, about 40% of the energy is carbon free. Then Google actually in this particular market contracted with firms to install additional solar. And so that bumped up their carbon-free energy usage to about 60% of their annual energy usage now came from solar and wind. And then they also looked at bumping that up even further with adding more wind into the market mix. And that would be projected in their modeling. This has actually not happened yet in this particular site. But the addition of large wind to the solar resource then allows them to get to about 90% carbon-free energy at this particular data center. So the point here is that getting to large fractions of carbon-free energy for a 24/7 demand requires a mix of generation technologies. So that issue has been looked at in a more academic sense by a group working out of UC Irvine. This is a busy plot. If you're interested in the details of this, I would encourage you to have a look at this paper by Shaner and Davis, published about 3 years ago. The bottom line is, if you want a low carbon electricity system that has a reasonably high reliability, and reliability here is defined as generation meets demand over some spatial scale, you're going to have large amounts of storage. They were estimating what happens to reliability if I built a system with 12 hours of storage. The horizontal axis in each one of these 4 plots is the area of energy generation aggregation, ranging from a scale of 1,000 square kilometers, like a small city, to a continental scale aggregation, that is national or continental scale transmission capability. And then the vertical axis on each of these plots is a mix from 100% solar, say at the upper left corner, to 100% wind at the lower left corner. And so you can see, if I just pick a combination, let's say I want a power system that has 95% reliability, and I'm willing to have a system that's, say, 50% solar and 50% wind. Well, then if I have a system with 12 hours of storage, I'm going to have to aggregate over reasonably small scales, around 10,000 square kilometers. That's not too hard to do. If, however, I don't have any storage in my system, it's impossible to reach the 95% reliability with a system with no such storage. I would point out that the US power system regulators require a reliability much better than 99%, typically 99.9+%. And so you can see that that level of reliability is not possible to reach with a combination of wind and solar only and a moderate amount, half a day of storage. I'm going to skip this slide in the interest of time. Simply suffice it to say, if you want NERC level that is 99.95% reliability, you have to overbuild your generation capacity by a factor of something like 3 to 10, depending upon the details of the system. So it just gets very expensive because you end up building a lot of renewable generation that most of the time you're not using. Jesse's work then really looked at what is the impact if I adopt other generation technologies, what Jesse termed firm low carbon or firm clean technology, into the generation mix. And the key finding from that result, of course, from Sepulveda and Jenkins et al., was that there was a very large drop in the average cost of electricity when you allowed these non-renewable but clean technologies into the mix, drops in factors of 2 to 10, depending on the details of the analysis, in the net cost of electricity to the consumer. So what lessons to draw from all this background? Well, there is clearly renewables are going to grab a larger and larger fraction of the electricity market, at least for I would say the next decade or so. But eventually there'll be some saturation of that, probably well below 100% of our electricity generation. Whether it's 50% or 80%, I think is difficult to tell. But there will be, in my view, a clear need for firm low carbon or zero carbon generation in this high renewables future. This generation, whatever this clean and firm generation is going to have to compete and survive in many cases, not everywhere around the world, but in many cases, in restructured, liberalized markets. If fusion is going to move into and compete in that market, it will have to be capable of surviving in those markets at the prices that it can fetch in those markets, and also recognizing that it's probably going to be operating in a load following manner, rather like the existing thermal systems are in areas where there's already a large portion of renewable energy, like California and in some regions of Europe. And finally, fusion is going to have to compete with other competing clean, firm generation technologies that have already emerged and begun to gain market share while we in the fusion world try to finish the development of fusion. So given that as background, what then does it take for a fusion system to compete in this market? Let's talk a little bit about that. The competition for this market, I think, is going to be a combination of natural gas, probably gas-fired turbines, and carbon capture and sequestration. This might be, for example, with the alarm cycle and supercritical CO2, perhaps advanced light water reactors, or so-called fourth generation or small modular fission reactors, There are many people who advocate that that technology will be attractive. Engineered geothermal energy, this is not your grandfather's geothermal energy. This is drill a very deep well of order 10 kilometers down, fracture the hot rock that you encounter, pump water down into that hot rock, make steam, recover the steam and make electricity from it. We know how to do that as well. You could use the excess renewable energy to make synthetic natural gas, so-called power to gas or power to hydrogen schemes. And then you put that gas or hydrogen into a distribution network, and then you burn it in conventional turbines. But it's now carbon-free because you've generated by without producing any net carbon emissions to the atmosphere. Or honestly, I think what's more likely to happen is, at least for a number of decades in the immediate future, we will continue to use fossil methane, fossil natural gas in conventional gas turbines, and will emit some carbon into the atmosphere. So fusion is going to have to compete against these kinds of technologies. Maybe somebody will dream up another technology, but these are the ones that I know about, at least. So the required characteristics of any such firm zero carbon generation technology is it has to be capable of ramping at a suitably rapid rate and load following. It's going to have to be profitable with fairly low utilization. That is, it's not always selling power into the market. It must have a reasonably low marginal cost of generation, not necessarily as low as renewables, but certainly lower than what we're used to today. There will likely be limits on the allowable capital expense for the technology. It must be safe and it must achieve widespread acceptance by the public. I'll skip that in the interest of time. So those are a few technologies that I was going to talk about. So to try to get a sense of what fusion would be, what fusion characteristics would have to look like in order to be economic, one would ideally have a system optimization study that takes into account the dynamics of the market, the costs of all the competing technologies and so on, and then looks at at what point does fusion get priced into the market. Unfortunately, there is no such study in the literature today. The closest thing that exists is the work that came out of the MIT study on the future of nuclear energy in a carbon-constrained world. This is essentially implicitly assuming that nuclear fusion is going to sort of look like a fission system. So the highlight results coming out of that study were that this is the result that for when they looked at the New England system. They also had some results from, I believe it was the ERCOT system down in Texas, but the results looked largely the same as the New England system. And so what they were looking at is, for a generation system that has a given amount of emissions per unit of energy produced, at what point does nuclear become an economic and cost-effective generation technology? So at today's carbon intensities of around a little bit less than 500 grams of carbon CO2 per kilowatt hour of energy produced, the answer is no nuclear is economic at that point. And at prices of nuclear that were assumed in the study of about $5,500 per kilowatt, or the so-called low-cost scenario of about $2,800 per kilowatt of capacity. And what they found is, as you dial down the allowable emissions, at some point, cheap, quote unquote, cheap nuclear prices into the market. And so you could see that, let's say at 50 grams of CO2 per kilowatt hour production, this optimization study suggests that half of the generation should come from the so-called cheap nuclear technology. But if the nuclear capex was actually roughly double, then there would be no market for that more expensive nuclear. I should add that current prices, based on the Vogtle experience, are well in excess of $10,000 per kilowatt. And so obviously conventional light water reactors are priced out of the market, and anything like a low carbon energy future, only when you get to very, very low emissions between 1 and 10 grams CO2 per kilowatt hour of energy does even expensive, that is $5,000 per kilowatt nuclear, become economic. So I would argue that until there's, and I understand that Jesse and some collaborators at Princeton, you guys are starting to work on a fusion specific version of this study. So I'll be interested to see the results of that when they are available. But right now it looks to me like if fusion is operating in a market that sort of looks like what it is in the New England area today, it's going to have very low capital costs of order a few dollars per watt. In addition to being cheap enough, I think fusion is going to have to avoid what has been termed in the I would say the risk literature as so-called dread risk that's associated with fission-based nuclear power. This plot is taken from this classic paper back in the late 70s, looking at the public acceptability of a very large number of technologies that we all use all the time, ranging from food coloring to surgical procedures to electric power, motor vehicles, and so on. And the main point here is that nuclear power fission occupies a very special place in the mind of many people in the public, in that the risks are both involuntary, that is, you and I living outside the power plant can do nothing to control the operation of the power plant. The consequences of a severe accident are immediate. They're hard for us to really predict. They are at least perceived to potentially be catastrophic or lethal. And so fission sort of sits in this very unenviable place in this parameter space. And there have been some recent studies by some of my collaborators at UCSD that shows that this dread risk does have, they did a very nice sociological study of the effect that this risk has on the acceptability of fission. And what they found is that when the audience was blinded to the fact that the technology was nuclear, but all the other attributes of the generation technology were shared with the audience, the acceptability, a large fraction of that audience, say 85% or so, would accept, about 40% more of them would accept the generation when they didn't know it was quote unquote nuclear. And as soon as they found out that they were talking about a nuclear-based technology, the amount of nuclear power in the portfolio that was acceptable to that part of the population dropped significantly. So the conclusion of those authors from this sociological studies a couple of years ago was that simply having probabilistically safer reactors, that is, you drop the probability from 10 to the minus 6 per reactor year of operation to 10 to the minus 7, which is kind of what the engineering community tries to do, is probably not enough. Somehow this dread risk has to be overcome. So now let's pivot to in the last few minutes that I have, talk a little bit about fusion. So obviously, if you've been paying attention at all in recent months, there's a huge amount of interest in the recent emergence of a privately funded fusion industry. I've shown just cover articles from a number of recent publications, and then taken the logos from all the fusion systems companies that I know of today, showing on the right. So there's clearly an interest in this possibility of new innovative fusion confinement schemes. I just pulled this out of the Nature article just to put things on one plot. So here's the conventional technology tokamak, the ITER scale device. These tiny little dots here are human beings. So this is an enormous, high capital cost, high unit size device. This is the so-called compact tokamak, that the ARC device that our friends up at Cambridge are pushing for. This is a cartoon of a third confinement scheme called the field reverse configuration out of TAE Technologies here in Southern California. This is the magnetized target fusion reactor that General Fusion is pushing. And this is the W7 accelerator in Germany to scale with human beings. This device would have to be scaled up considerably to become a power reactor. The point is that there are many, many pathways to fusion that are now being pursued by the private sector. These folks, as of a week ago, when CFS announced a $1 billion funding round, they've now attracted $4 billion of private money to date, and they have very aggressive goals and schedules. However, it's important to remember now the fusion physics. The requirement that this triple product, that is the pressure of the fuel times the energy confinement time, has to exceed a critical value. And that critical value is illustrated by these solid lines up here. All these dots are various experiments as a function of year. I would refer you, if you're interested in the data where this comes from, there's a very nice Jason's report from about 2 years ago that came out. So this red curve is the tokamak line. This black curve is the laser fusion line. The green curve is the line. Here's the so-called spherical tokamak approach Princeton is pursuing, and then various other approaches. Some of the privately funded fusion schemes are generally down here on this plot. And it's important to note that this is a semi-log plot, and going from this line to this line is a factor of 100 increase in this parameter. So most of these, not all, but most of these privately funded entities, with the exception of the high field tokamaks, are somewhere between 3 and 4 orders of magnitude. That is a factor of 1,000 to 10,000 away from this break even and then ignition criteria. The one standout are the high field tokamaks, the group CFS group out of Cambridge, and then a group in the Tokamak Energy in the UK, who are quite close to the anticipated conditions for energy break even and then burning plasmas. The other thing to note is that we are also very far away from the operational space that any conceivable reactor will have to operate. And here I'm showing the achieved triple product on the vertical axis versus the experiment duration. And you'll see that our hero plots that we all like to, in the fusion community, like to point to, are for periods of time like 1 second. Whereas a reactor needs to be out here at somewhere between several hours and several weeks or even months of operation, depending upon its integration with the electricity grid and the market. So there's a huge gap between where we are and where we have to go. ITER will certainly move us along that curve, but there will still be a gap remaining after ITER. I use this simply to note that there are going to be very significant nuclear technology challenges that must be resolved to enable fusion as a useful energy production technology. Some of those technology needs, they're all clearly recognized in the fusion community. We got to learn how to handle the particle and heat that's leaving the reactor, no matter what confinement scheme you use. It presents huge challenges to the materials of the reactor wall. The reactor wall materials must also last long enough for economic operations. In other words, if you have to replace the wall every 2 weeks because it's falling apart because of radiation damage, your system's probably not going to be economic. You've got to develop and then demonstrate adequate tritium handling so that you can close the fuel cycle. To have, I think, a publicly acceptable fusion technology, I think is going to have to be built out of low activation structural materials so that when you decommission the device, you do not have long-lived isotopes that have to be isolated for millennia. And then finally, you've got to integrate and demonstrate all these technologies into a working reactor. And then only after you've done all of these things can your reactor begin to try to aim to move into the marketplace. So if I stand back now and I look at what are the implications for an economic fusion system, I think it needs to have the right system size. The old 1 gigawatt class systems, I don't think will be attractive at least in the liberalized markets. I suspect that system size will sort of look like today's combined cycle gas turbines. They can ramp over a wide range of operating powers, perhaps integrate with thermal storage. Low capital expense, that is a few dollars per watt, is going to be needed. It has to be profitable with low spot prices on the market of a few tens of dollars per megawatt hour and probably less than 50% utilization. It's got to be reliable and maintainable, inspectable, and it's got to avoid nuclear's dread risk. And then finally, I'll close on this point. Once all of these characteristics have been demonstrated for fusion, only then will it begin to move into the market and try to climb up this so-called market fraction S curve. Fusion right now is not even on this plot, which is market fraction on the vertical axis versus time or cumulative production. So we're going to still have to climb this curve. And historically, it has taken energy technologies several decades to move up this curve. And so my conclusion, which is I regret saying this as somebody who spent a lot of time on fusion. I think the implication is that if fusion reactors can be shown to work in the, say, let's be optimistic, in the late 2030s, at best, they will need until well after the mid-century before they have a few percent market share. This is after climate science tells us that we must get to net zero, or at least net zero CO2 emissions. And then I conclude that I think in the nearer term, that between now and the middle of the century, fusion will probably work, but it's unlikely to contribute to our initial decarbonization needs, but that it may have a role to play later in the transition to provide a long-term carbon-free power source that we can use in concert with other technologies to meet our energy needs. And with that, I will stop.
Thanks, George. So we're a little bit over time past our initial 12:30 stop time. So if others have the freedom to stick with us, we'll maybe take one or two questions here before we wrap up. Maybe put on your pitch hat. Think that you're pitching fusion technology to an investor.
Okay.
Egeman's asking here, what do you think separates fusion from other gigawatt scale or carbon-free firm resources? So what would you say would be like the differentiating factor, special sauce, that should make us excited about these kinds of investments?
As a nuclear technology, it has the potential, if we do things right, to avoid the production of truly long-lived nuclear waste. Long-lived meaning like many, many thousands of years or longer. But that's only if we develop the right materials. So I think that's one thing. If I move away from nuclear-based technologies, the fuel for it, deuterium and lithium, which is the raw input, are widely available, and there's plenty of them out there for as far as we can imagine to use into the future. The only other non-nuclear technology that sort of meets that, I think, is engineered or deep geothermal. So I would say that's probably the other sort of attractive attribute in my opinion.
So like nuclear, but better.
like a fission, but better. Yeah.
Are there any questions in the audience at Mader Hall?
I see a few on the like in the chat.
Well, hearing none from the audience there, then let's just, I guess, one final question, which is there, from Egeman as well, is there anything that could change your conclusion here, which he notes is also the conclusion from the ITER Director General on the timeline? What would it take to, to have fusion add up to something more in the 2050 timeframe?
You mean to accelerate this so that it has a significant fraction before the 2050?
Yeah.
I think the only way that I could see something like that happening is if we sort of are in the sort of a laissez-faire approach to developing clean, firm technologies, it would have to switch to something like a wartime footing, an existential threat, where you pour everything you've got into every single approach that might work, and then you see how it plays out. People in the fusion community have talked about something like that off and on for many decades. I honestly don't see any evidence that thing is actually happening. So I think that's the only thing that would change my conclusion.
Great. Well, thanks so much for joining us, George. It's been a pleasure to hear your thoughts on this rapidly growing sector, and thanks for the deep thinking here. I look forward to continuing the conversations about how we can combine insights from the fusion community and the energy systems community to provide some greater direction here. So thanks for joining us, and thanks to our audience as well, virtual and in person. Hope everybody has a great day and stay healthy.
Thank you, Jesse. Thank you for the invitation.